In the previous lecture, we have discussed about alcohols, the classification and nomenclature of alcohols. We discussed the preparation of alcohols. In the preparation of alcohols, we discussed the commercial methods of preparation also, from petroleum, from natural gas, or from fats and oils also. Then we discussed the laboratory preparation of alcohols via the reduction of aldehydes and ketones, carboxylic acids, esters, acid chlorides and anhydrides. We also discussed the selective reduction to produce alpha beta unsaturated alcohols in the earlier presentation. Now, in the present discussion, we are going to discuss the physical properties of alcohols and we are going to discuss some of the chemical properties of alcohols. The outline of the present lecture is, we will discuss here the physical properties of alcohols, in which we are going to discuss dipole moment, we are going to discuss intermolecular hydrogen bonding, solubility, then we will discuss acidic nature of alcohols, we will discuss basic nature of alcohols and the reactions of alcohols. Physical properties of alcohols. Alcohols actually are the composite of alkanes and water. As you can see here that if you replace the H of alkane by OH, then alcohol results. Alcohol contain alkane like alkyl group and water like hydroxy group. The hydroxy group gives alcohol their characteristic physical properties like polarity, solubility, high boiling point, etc. Whereas alkyl group modifies these properties depending upon their sizes and shape. Dipole moment. We will now discuss dipole moment shown by alcohols. Alcohols exhibit considerable dipole moment due to the presence of electronegative oxygen next to the alkyl group. When oxygen is attached to carbon, since there is electronegativity difference between carbon and oxygen, dipole develops on the two atoms. The amount of charge on the two atoms multiplied by the distance between them decides the dipole moment of that particular bond. The dipole moment is represented by the term mu, which is equal to E, the charge, multiplied by d, the distance, and the unit of dipole moment is dBi, capital D. The net dipole moment of a molecule is the vectorial addition of individual bond moments and is represented as follows. Actually, in a molecule there are many bonds. So, when we have to discuss or when we have to see the dipole moment of that particular molecule, the net dipole moment will be the vectorial addition of individual bond moments, and a dipole moment is designated by an arrow drawn in the direction of dipole with the arrowhead at the negative end and positive at the positive end. As you can see here in this alcohol molecule, the arrowhead is showing towards oxygen, which is more electronegative, and the back side of our arrow or positive side is towards carbon, which is less electronegative. We will now discuss intermolecular hydrogen bonding. Since we have in alcohol oxygen attached to hydrogen, oxygen is electronegative and hydrogen on the other hand is less electronegative, as well as it is very small in size. As a result, the poles are generated between O and H bond. As a result, the oxygen of one alcohol molecule attracts the hydrogen of another alcohol molecule and results in the formation of hydrogen bond. A hydrogen bond is represented in the form of a dotted line. As you can see here, between two alcohol molecule, there is a dotted line showing the hydrogen bond between the two alcohol molecules. The intermolecular association of alcohol molecule through hydrogen bond leads to higher boiling point of alcohol as compared to the alkanes, alkyl halides and ethers of comparable molecular mass. With the help of examples here which are shown in the slide, you can understand this point very easily. See, normal pentane has molecular mass 72, diethyl ether 74, normal propyl chloride 79, and that of normal butyl alcohol 74, almost similar molecular masses of all the 4 molecules. But when you look at the boiling point of these molecules, you will find that normal butanol has very high boiling point as compared to these 3 molecules. The reason behind it is the association due to intermolecular hydrogen bond in case of normal butyl alcohol, which is not possible in any of the other molecules. Alcohols show increase in boiling point with the increase in carbon chain. Another factor, alcohols show decrease in boiling point with the increase in branching in carbon chain. These 2 points we will elaborate upon in the next slide. Here in this table you will see that we have here methanol, ethanol, propanol and pentanol. These 4 alcohols are normal chain alcohol. The only difference is that the number of carbons are increasing. When the carbons are increasing, there is a periodic increase in the boiling points. Now look at the example of butane 1-ol, butane 2-ol and 2-methyl propane 2-ol. These 3 alcohols have similar molecular mass. They have similar molecular atomic structure C4H10, but you will see the difference in their boiling point. Why is this boiling point difference seen in these molecules? The reason behind it is the branching in carbon chain. More the branching, less will be the boiling point of the molecule, and this you can see in these examples. We will now discuss the reason for high boiling points shown by alcohol. The alcohols have high boiling points because they are associated liquids. As a result, higher energy is required to break the hydrogen bond that holds the molecule of alcohol together. We will now discuss the solubility of alcohols. The lower alcohols up to 4 carbon atoms are soluble in water as they form hydrogen bond with water molecules, as seen here in over here. You can see one alcohol molecule and another is water molecule, then alcohol, then water, and so on, so forth. That is why the alcohols are soluble in water, but the alkyl chain increases. Higher alcohols having large non-polar alkyl groups are insoluble in polar solvents like water, but soluble in non-polar solvents like benzene. Diols and triols are the alcohols having 2 and 3 alcoholic group. Diols and triols provide more than one site per molecule for hydrogen bonding. As a result, they have higher solubility in water. The simplest diol, 1,2-ethane diol, has very high boiling point also, and that is to the tune of 197 degrees centigrade. Ethylene glycol is used as antifreeze because of its properties like high boiling point, low freezing point and high solubility in water. This is the molecule of ethylene glycol having 2 hydroxy groups. Let us now discuss the acidic nature of alcohols. Acids actually are the compounds or molecules which provide H+ ions in solution. In alcohol, hydrogen is bonded to a very electronegative element, oxygen. The polarity of oxygen hydrogen bond facilitates the removal of hydrogen. Also, the negative charge on oxygen of alkoxide is readily accommodated. You can see here this alcohol molecule, when OH bond dissociates, there is formation of alkoxide ion. The negative charge on oxygen is stabilized. As a result, the conversion of alcohol into alkoxide and H+ is facilitated, or in other words we can say alcohols act as acids. Alcohols have acidities similar to that of water. You can see here from the pK values of different acids like methanol, water, ethanol and tertiary butanol. As seen in the above table, methanol is slightly higher in acidity than water. Also remember, any factor that stabilizes the conjugate base of an acid increases its stability. We will discuss the conjugate base of these acids in the next slide. Tertiary butanol, on the contrary, is less acidic than water and methanol due to solvation effect. Solvation effect is the stability of cations and anions formed upon dissociation by the solvent molecule. The water molecule solvates the alkoxide ion formed from alcohol by removal of a proton. Solvation stabilizes the alkoxide and increases the acidity. If the alkyl group is bulky, the solvation is hindered and is not effectively stabilized. Decreasing order of acidic strength of alcohols therefore is follows the order, like primary alcohols are most acidic, then are secondary alcohol, and then are tertiary alcohol. So, the reason behind the alcohols to show acidic character is the dissociation of oxygen hydrogen bond, and second is the solvation of the alkoxide generated by the solvent. The acidity of alcohols can be demonstrated by the reactions of alcohol with active metals. Hydrogen is liberated during the process. You can see here that alcohol is reacting with sodium metal, forming alkoxide, and hydrogen gas is liberated. The product alkoxide is a strong conjugate base of the weak acid alcohol. The alkoxide obtained from ethanol is called sodium ethoxide, and from tertiary butanol is called sodium tertiary butoxide. Now, we will discuss just how acidic are alcohols. We have already seen that alcohols are less acidic than water molecule, but look at the order of acidic strength of alkynes and alkanes. You can see here that alcohols are more acidic than alkynes and alkanes. How are we going to justify this? If alcohol react with sodium salt of sodium alkylides, then there is formation of this sodium salt of alcohol, and alkynes are liberated from their salts. So, this shows that alcohols are more acidic than alkynes. Similarly, alcohols are less acidic than water because sodium salt of alcohol is converted into alcohol during the reaction of sodium alkoxide with water. We shall now discuss the basic nature of alcohols. Bases are the compounds which can accept proton. Here, in case of alcohol, we all know that alcohols are ROH molecule. Oxygen has lone pair of electron on it. Now, if alcohol react with acid, they get protonated, they get proton from the acid, form the protonated alcohol, and the salt is formed. So, alcohols are Lewis bases as they have lone pair of electron on oxygen. Like water, alcohols are basic enough to accept proton from its strong acids like sulfuric acid and hydrochloric acid. The basic nature of alcohols is influenced by the alkyl group attached to the carbon having hydroxy group. Alkyl groups having plus I effect increases the electron density on oxygen, thereby increase the basic strength of alcohols. In primary alcohol, there is only one alkyl group attached to the carbon having hydroxy group. Here we have two alkyl groups, and here three alkyl groups are there. More the number of alkyl groups, more will be the electron release and more will be the basic strength of alcohol, and that is why the increasing order of basic strength of alcohol is primary alcohols are least basic, then are secondary alcohol, and then are the tertiary alcohols. You are already aware that conjugate basis of an alcohol is called alkoxide ion. The alkoxide ion can be prepared from the reaction of alcohol with sodium or potassium metal. Since most of the alcohols are weaker acids than water, most alkoxides are stronger bases than the hydroxide ion, and hence this is the order. You can see that alkoxide ions are more basic than the hydroxide ion. Alkoxide being strong bases are used in nucleophilic substitution reactions. Here ethoxide ion reacting with ethyl bromide to give diethyl ether. We will now discuss the reactions shown by alcohols. Alcohol molecules show basically three kind of reactions. In the first kind of reactions, the reaction which involve acidic nature of alcohols or where the cleavage of oxygen hydrogen bond takes place. In the second kind of reaction, the reactions involve basic nature of alcohols and where the cleavage of carbon oxygen bond takes place. And in the third kind of reaction, the reaction involves the entire alcohol molecule. Here we will discuss some oxidation reactions shown by alcohols. Now the reactions involving replacement of hydrogen or reactions where alcohols act as acids. When alcohol react with active metals like sodium or potassium or with metal hydride, they form metal alkoxide. This ethanol molecule when react with potassium metal, it forms potassium ethoxide along with hydrogen gas. Tertiary butanol when react with sodium hydride, it forms sodium tertiary butoxide along with hydrogen gas. Primary alcohols being more acidic than secondary and tertiary alcohol undergo this reaction faster. Also the alkoxide of primary alcohol is better stabilized by solvation. Let us now discuss the reaction of alcohols with carboxylic acid. When alcohols react with carboxylic acid, esters are formed. Reaction occurs in presence of dilute sulfuric acid or dry hydrogen chloride gas. If the reaction takes place in presence of dry hydrogen chloride gas, the reaction is called Fischer-Spear method for the esterification. Here ethanoic acid or acetic acid reacting with ethanol in presence of acid to form ethyl ethanoate an ester. This is propanoic acid reacting with ethanol forming ethyl propanoate. Reaction of alcohol with acid chloride and acid anhydride. When alcohols react with acid chloride or acid anhydride in presence of acid, they again form ester. Here it is ethanol and ethanoyl chloride forming ethyl ethanoate along with hydrogen chloride. It is ethanol and ethanoic anhydride reacting in presence of acid to give ethyl ethanoate along with acetic acid. Let us now discuss the reaction of alcohol with Grignard reagent. Alcohols being acidic in nature react with Grignard reagent to form alkanes. When we react ethyl magnesium bromide with ethanol, the product is ethane. If we take a different alkyl magnesium bromide, the product will be a different alkane. The reaction of alcohol with sulfonyl chloride. Alcohols react with alkyl sulfonyl chlorides to form sulfonate esters. This is a good method to convert the alcoholic hydroxy group to a better leaving group. Actually, the hydroxy group of alcohol is quite basic in nature and is not a good leaving group. But if we convert it into alkyl sulfonate, then it becomes a good leaving group. We will discuss about this property of alcohol in the reactions of alcohols. Well, in the present discussion, we have so far discussed the physical properties of alcohols due to the change in their structure. We have discussed the dipole moment, we have discussed boiling point, intermolecular hydrogen bonding and solubility of alcohols. We have also discussed the acidic nature of alcohols, basic nature of alcohols, and we have discussed certain properties of alcohols where they have acted like acids. In the next presentation, we will discuss the properties of alcohols where they will act as base. We will also discuss some oxidation reactions of alcohols. Thank you.